The event horizon of a black hole is often described as a point of no return, a boundary where everything suddenly stops, freezes, or is violently destroyed. This image is powerful, dramatic, and deeply misleading. In reality, the event horizon is not a physical surface and not a place where anything special suddenly happens. It is a boundary defined entirely by the structure of space-time itself. To understand what really happens at the event horizon, we first need to let go of familiar ideas. There is no wall, no membrane, and no glowing edge surrounding a black hole. The event horizon is not something you could touch or see directly. It is a geometric boundary, defined by which paths through space-time still allow escape and which do not. Far away from a black hole, space-time behaves almost normally. Objects move, light travels, and time flows in ways that closely resemble our everyday experience. As you move closer to a black hole, gravity becomes stronger, but nothing dramatic happens at first. There is no sudden increase in force, no warning sign, and no visible marker showing where the event horizon will be. From the perspective of someone falling toward a black hole, the event horizon is not a special location. If the black hole is large enough, tidal forces near the horizon can be extremely small. An observer falling freely would cross the event horizon without feeling anything unusual at that exact moment. Physics does not suddenly break down there. This is one of the most counterintuitive aspects of black holes. From the outside, however, the story looks very different. A distant observer watching someone fall toward a black hole never sees that person cross the event horizon. Instead, the falling object appears to slow down. Its motion becomes increasingly sluggish, and the light it emits becomes more and more redshifted. Over time, the object fades and disappears, never quite reaching the horizon from the external point of view. This difference is not an illusion and not a contradiction. It is a consequence of how time behaves in strong gravitational fields. Near a black hole, time passes at different rates for different observers. For the falling observer, time flows normally. For the distant observer, time near the horizon appears to slow almost to a stop. The event horizon, then, is not defined by a dramatic physical event. It is defined by causality. Beyond this boundary, no signal, no information, and no influence can ever reach the outside universe. Light emitted inward cannot return. Paths that once allowed escape no longer exist. This is why the event horizon is called a horizon. It marks the limit of what can be seen or influenced from the outside. Inside the event horizon, the structure of space-time changes in a profound way. Directions that once pointed through space begin to behave like directions through time. Moving inward becomes unavoidable, just as moving forward in time is unavoidable in everyday life. There is no choice involved, no thrust or maneuver that can prevent this progression. This does not mean that objects are pulled inward by an infinite force. It means that space-time itself has been reshaped so completely that all possible future paths lead deeper inside. The geometry of reality determines the outcome. At the center of a classical black hole lies what is called a singularity. This is not a place where matter piles up in a simple way. It is a region where space-time curvature becomes extreme, and our current theories stop providing reliable predictions. The singularity is a sign that our understanding is incomplete, not a confirmation that reality ends there. Importantly, the event horizon is not the singularity. The horizon is a boundary. The singularity is a region deeper inside. Confusing the two leads to many misunderstandings about black holes and what happens near them. Another common misconception is that black holes actively pull objects in once they cross the horizon. In reality, nothing special changes at that boundary for the falling object. The motion continues smoothly, governed by the same physical laws as before. The difference lies not in forces, but in what paths through space-time are still available. This distinction is subtle but crucial. The event horizon does not mark the end of physics. It marks the limit of observation. Beyond it, events still occur, processes still unfold, and time still passes for anything that falls inside. What changes is our ability to receive information about those events. This is why black holes challenge our understanding of information, time, and causality. They force us to confront the idea that reality can continue in regions forever hidden from the rest of the universe. Nothing magical happens at the event horizon. Nothing suddenly breaks. Nothing explodes or freezes in place. The boundary is real, but its effects are subtle and deeply tied to how space-time itself works. The event horizon is not a wall. It is not a surface. It is not a moment of destruction. It is a boundary of possibility, written into the geometry of the universe itself. And next, we'll look at one of the most famous questions in physics. Does time really stop at a black hole?